So in this lecture, I'm going to be explaining another important article about event extraction, which is called Learning from a Friend, Improving Event Extraction via Self-Training with Feedback from Abstract Meaning Representation. So we are using this semantic parsing algorithm, AMR, to use it. We want to use it for event extraction. So this paper in 2023, data scarcity has been the main factor that hinders the progress of event extraction. To overcome this issue, we propose a self-training with feedback framework that leverages the large-scale unlabeled data and acquires feedback for each new event prediction from the unlabeled data by comparing it to the abstract meaning representation graph of the same sentence. Specifically, this self-training feedback consists of a base event extraction model training on existing event annotation and then applied to large-scale unlabeled corpora to predict new event mentions as pseudo-training examples, and a novel scoring model that takes in each new predicted event trigger and argument, its argument role, as well as their path in the AMR graph to estimate a compatibility score indicating the correctness of the pseudo label. The compatibility scores further act as feedback to encourage or discourage the model learning on the pseudo-labels during self-training. So first we give it to AMR parser for event extraction model and the event extraction model, and then we give it to this scoring module. This is a scoring module that it has self-attention, linear sigmoid, and then so the event extraction task consists of 3 subtasks: event detection, argument identification, and argument role classification. Given an input sentence, event detection aims to identify the span of an event trigger and assign a label where tau denotes the set of target event types. Argument identification aims to find the span of argument in W. An argument role classification further predicts a role that the argument plays in an event. So we select 1E and AMR-IE as base models given their state-of-the-art performance. So the training objective is to minimize the gap between these 2 global feature scores denoted as LG. And the rest of that is just argument classification, trigger classification, argument identification, trigger identification, the 4 classic things that we need to do. But this extra global feature score is computed for the predicted information graph and the goal annotation. So for what is a scoring module? Our scoring model takes AMR graph as a reference motivated by the observation that an event structure usually shares similar semantics and network topology as the AMR graph of the same sentence. Thus, their compatibility can be used to measure the correctness of each event structure. This observation has been discussed and shown effective in previous studies. However, previous studies directly take AMR graph as input to the extraction model and thus require AMR graphs during both training and inference, making their performance highly dependent on the quality of AMR parsing. Different from them, our proposed SDF only takes AMR graphs during the reference to measure just the correctness of the event prediction during self-training, making it free from potential error propagation from AMR. Because if your AMR has problem, has some error, then it propagates the error of prediction to the downstream, which is a bad thing. That's why this paper is using it just for understanding and self-training, not for inference. So at the inference, we don't need to worry about AMR. Given a sentence W tilde from unlabeled corpus and a predicted triggered tau sub I tilde, we aim to estimate the correctness score for each pair of trigger and argument prediction based on compatibility with their path in the AMR graph. Thus, we first apply state-of-the-art AMR parsing tool to generate the AMR graph. And we follow and group the original set of AMR relation into 19 categories. Thus, E sub ij denotes a particular relation category, and R denotes the set of AMR relation categories. So, given a predicted tau sub I and its type, a predicted argument and its argument rho, the scoring module estimates their correctness by this concatenation as input and outputs a compatibility score. To estimate the compatibility between the event trigger and argument prediction and their path in the AMR graph, we apply multi-layer self-attention over the joint representation of AMR path and the event prediction to learn better contextual representation for the sequence. And we add the position embedding before feed it into the self-attention layers. Finally, we compute an overall vector representation from average pooling and feed it into a linear layer and a sigmoid function to compute a probability indicating the correctness of the predicted event trigger and argument. We optimize the scoring model based on the binary cross-entropy objective. So y is just a binary label that indicates the argument role is correct or not. And psi here is just the parameters of the scoring model. During training, we have goal triggers and argument as positive training instances, and we swap the argument roles in positive training instances with randomly sampled incorrect labels to create negative training instances. After training, the scoring model will fix its parameters and apply it to its self-training. To improve the base event extraction model with self-training, we take the new event predictions from the unlabeled corpus as pseudo samples to further train the event extraction model. The gradients of the event extraction model on each pseudo sample these are the gradients, but the theta here is just the parameters of event extraction model. But due to prediction errors of pseudo-labels, simply following the gradients computed on pseudo-label can hurt model's performance. Thus, we utilize the correctness score, C sub ij, predicted by the scoring model to update the gradients based on the motivation that if an event prediction is compatible with the AMR structure, it's likely to be correct. And we should encourage the model learning into pseudo-label. On the other side, if an event prediction is incompatible with its AMR structure, it's likely incorrect, and we should discourage the model learning on the pseudo-label. If the scoring model is uncertain about the correctness of the event prediction, we should reduce the magnitude of the gradients learned from the pseudo-label. So we then apply the compatibility scores as feedback to update the gradients of the event extraction model on each pseudo-sample during self-training. To improve the efficiency of self-training, we update the event extraction model on every mini-batch, and to avoid the model diverging, we combine a supervised training and self-training, so the overall loss is the summation of them. And the beta is just a combining ratio. L sub E is computed on a labeled dataset, but this is just pseudo-label instances from X sub U. So this is a qualitative results. We say, for example, the predicted average score and the goal argument, predicted argument. And we use it for ACE 25, but also for ERE English. And you see state of the art is still low. For example, for this data set, for argument classification, we have this score, which is low. So these are sentences. You see their AMR pass and the argument row, and then the compatibility scores computed by scoring models on the development and test set. And we have 3 data sets. This one, 2 of them are ACE, and the third one is ERE English. But any ACL paper has some limitations. Our method utilizes AMR annotation as additional training signal to alleviate the data scarcity problem. In this problem setup, generally speaking, AMR annotations are more expensive than event extraction annotations. Nonetheless, in reality, the AMR data is much bigger than any existing event extraction datasets. And AMR parsers usually have higher performance than event extraction models. Leveraging existing resources to improve event extraction without incurring additional costs is a feasible and practical direction. Our work has demonstrated the effectiveness of leveraging the feedback from AMR to improve the event argument extraction. However, it's still underexplored what additional information and tasks can be leveraged as feedback to improve trigger detection. We did not have quantitative results for alignment between AMR and event graphs. The authors randomly sampled just 50 event graphs from ACE 25 event graphs and found 41 are aligned under AMR graphs based on human judgment. But in future work, more systematic studies should be conducted to evaluate the alignment. There is a large gap between the validation and testing dataset in terms of label distribution. We observe that the performance. So here we have a label shift in the context of domain adaptation, which is really interesting.